You had me worried for a minute. I thought it was the wrong place with your introduction. Well, I think the timing couldn't have been better. The encounter has started, the images are coming in, and Voyager has begun the sixth and last of a decade's worth of encounters with the outer planets. Today what I want to do, rather than giving you a comprehensive overview of what we're planning to do at Neptune, what I want to do is try to relate some of the things that we may learn to some of the things we've already learned. And I hope in the process convince you, if you need convincing, that this sixth encounter is likely to be as exciting as the previous five. So if I can have the first slide, just to remind you, many of you don't need reminding, but some may, if we could have the lights down a bit so that the slide shows up better. There are two classes of planets in the solar system: the inner rocky objects, terrestrial planets, of which the Earth is best known, and the outer giant planets, which are quite different in character, having rocky cores, most likely molten rocky cores in some cases, but mainly gas. And melted water ice in the case of the most outer two. You notice we have two sets of twins. We have Jupiter and Saturn, which rather resemble each other, and Uranus and Neptune, which rather resemble each other. Now, the differences in these planets is related to the fact that they formed further from the Sun, where the temperature at the time they formed, and this is obviously just a model, the temperature at Jupiter at the time it formed was thought to be around 155 Kelvin, that is degrees centigrade above absolute zero, about minus 120 degrees centigrade. Water was in frozen form, so there was solid water ice, which could be accreted to form the cores of these giant planets. That was not the case in where the terrestrial planets formed. Water was in vapor form and therefore wasn't available to make up the bulk of the solid object. There's much more water in the universe, by the way, or in the solar system, than there is rock. Silicate materials. At Saturn, and of course it was at Jupiter where we saw our first planet-sized objects, Ganymede and Callisto, which are the same size as the planet Mercury, which are in fact half water ice. As we ventured on out to Saturn, temperature was still lower yet at the time Saturn formed, and that ice could have also incorporated ammonia. And indeed, it was and ammonia, of course, is a combination of nitrogen and hydrogen, and it was indeed at Saturn where we flew by Triton, which has an atmosphere which is predominantly nitrogen. At Uranus, colder yet, the ice could not only absorb ammonia and retain it, but also methane. And in fact, we noticed that as we flew by Uranus that indeed there is an excess abundance of methane, natural gas, in the atmosphere of Uranus. And there may well be some evidence, although no direct evidence, that methane was incorporated in the icy satellites. And finally, Neptune. We're visiting Neptune in just 3 months. And the temperature there was so cold that methane was frozen, so that in fact methane could have been incorporated as solid material as effectively as the water ice. And indeed, we know already from ground-based observations that its major moon, Triton, has methane on its surface and in its atmosphere. So it's been a journey to increasing distances in the solar system and systematic changes in the composition of the planets and the satellites associated with the environment in which they originally formed. These are Voyager images of Jupiter, Saturn, Uranus, and Neptune, all to scale, and to scale an image of Earth, again to illustrate the fact that these are indeed giant outer planets. The color of Uranus and Neptune already tells us that, in fact, their composition of the atmosphere is quite different. The excess abundance of methane absorbs in the red, and the net result is the sunlight, which reflects back, is deficient in red and therefore the object looks blue-green. When we look at these giant planets, of course, we're not looking at solid surfaces. There probably isn't a solid surface anywhere in the planet, but we're looking at clouds which form at the top of a very deep atmosphere. In the case of Jupiter and Saturn, an atmosphere mainly of hydrogen and helium, which extends deep inside the planet. And one of the four topics I want to touch briefly on is the details of the atmospheric motions, atmospheric dynamics in the planets, in these giant planets, which are really rotating spheres of gas and liquid. The second topic I want to touch on briefly is some of the peculiar aspects of the magnetic fields of these giant planets. Third, I'll talk a bit about the rather different ring systems which we find about these outer planets, and then I want to end with a discussion of Triton as an unusual satellite. So first, atmospheres. As I said, we're looking at clouds. In the case of Jupiter, of course, the temperature inside a planet is 10,000 degrees, and it gets cooler as the atmosphere rises, and eventually the temperature as the gas rises, being heated from underneath, rises. It reaches a temperature, in this case at about 6 or 7 atmospheres, where water will form a cloud. And above that cloud, there's very little water in the atmosphere. Similarly, as one rises, we have additional cloud layers form, the top cloud layer forming being ammonia ice crystals, and above that there's relatively little ammonia, mainly hydrogen and helium in this part of the atmosphere, and a trace of methane which has not yet frozen out or formed a cloud in the case of Jupiter and Saturn. In the case of Uranus and Neptune, they're both very similar in temperature, even though they're different distances from the Sun. The ammonia cloud, or perhaps there's actually a hydrogen sulfide cloud layer down here, we don't know, forms much deeper in the atmosphere because it's colder, and its freezing point, if you like, is deeper, therefore. And it's cold enough that the methane, as it rises, eventually does get cold enough to form a cloud deck. So when we look at Uranus or Neptune, we're most likely looking at clouds of methane ice crystals, not ammonia ice crystals, as was the case for the inner two of the giant outer planets. Now, one of the interesting problems is the formation of the belt and zone systems, which are so obvious that the cloud patterns on Jupiter and Saturn, at least, are organized into latitudinal belts and zones. And before the Voyager encounter, one suggestion was that these belts and zones were associated with jet streams. That is, as the material would rise, being heated from below, it would rise, form the cloud layer, and then that material, which is at a somewhat elevated altitude, would like to fall directly down into the adjacent belt region, both north and south. But because of the rapid rotation of the planet, just as storm systems here on Earth end up being cyclonic or anticyclonic, in this case, the atmosphere is deflected toward the east on the northern edge of the zone and toward the west on the southern edge of the zone in the northern hemisphere. And so the prediction was, and this is a weather system which would then be somewhat like, if you like, a thin layer weather system where the belt and zones and high-speed jet streams were all confined to a thin upper layer of the atmosphere where these clouds were forming. That was a prediction of a model which Andy Ingersoll had developed. And one of the things which we wanted to do then was to measure the winds, very detailed wind patterns, to see if they were indeed correlated with the obvious belt and zone cloud structure. On Saturn, the belt and zone pattern is much more subdued, and there was even less information from the ground with respect to any jet streams, although on Jupiter there was some information that did provide some indication of a correlation. Well, with Voyager, we managed to measure the winds. This black line is the winds in miles per hour. This would be eastward wind here, westward wind there, for instance, about minus 100 miles per hour. A strong eastward jet at the equator of about 200 miles per hour, and a westward jet, eastward jet. And you can see a resemblance, if you like, to the cloud pattern, which did tend to coincide with this thin layer model of the formation of the clouds and the wind patterns on Jupiter. At the case of Saturn, however, the situation seemed to be was somewhat surprising. That is, the winds at the equator of Saturn, rather than being a mere 200 miles per hour, were more like 1,000 miles per hour. And this eastward jet stream persisted over almost 30 degrees, plus and minus 30 degrees in latitude, unlike the case at Jupiter. And there was no apparent strong correlation between the jet streams and obvious latitudinal features in the cloud decks. That led Ingersoll to propose a much more radical view of atmospheric motions, which is illustrated in this slide. That is that, in fact, the atmosphere, since the object is really all fluid, all gas, maybe it's not just the top thin layer which has winds in it, but the entire interior has winds in it, and those winds are organized in concentric cylinders. So you can imagine one cylinder making up the equatorial region of the planet, which is rotating with a steady wind in this direction. Nested inside of that is another cylinder of fluid or gas rotating at a somewhat different speed, and inside of that would be still a third cylinder. And that the wind patterns which we see are just the exposed ends of these rotating concentric cylindrical wind systems. A rather radical view based on some laboratory work that Busa had done at UCLA some years ago, which tended to suggest that such a pattern might exist. Well, of course, one interesting question is, having developed this idea to try to explain the differences between Jupiter and Saturn, try to combine them into a single model, can one apply this to any other of the giant planets? In the case of Uranus, unfortunately, there was very little to see. The cloud deck, methane cloud deck, is deep enough that it was not visible. We saw a few plumes here and there, which allowed us to measure winds. And to first order, it does not have a strong jet stream structure like Jupiter and Saturn. But there's one important difference about Uranus. Jupiter, Saturn, and Neptune all radiate twice as much heat as they absorb from the sun. That is, they have an internal heat supply which is heating the atmosphere from below. In the case of Uranus, it radiates only a few percent more energy than it absorbs from the sun, and so it evidently is a very stably stratified atmosphere, not being heated from below strongly enough to cause it to convect, to essentially for the atmosphere to rise. And the net result is a rather different weather pattern, one which more resembles that on Earth, actually. Well, besides the belt and zone pattern, which in this cylindrical map now of Jupiter, you can see quite strongly. This is 360 degrees from here to here. There was another key characteristic of Jupiter, which we found with Voyager, and that is, for instance, this series of plumes, which are believed to be upwellings, thunderheads if you like, where the source is at the small point of the plume, and then much like a steamship, the plume material trails behind the smokestack, if you like, the place where the material is upwelling. That was one major characteristic, and you can see many such plumes, eruptive features. Another characteristic of this giant atmosphere was the presence of all these small cyclonic and anticyclonic storm systems. You can see literally dozens of them. You see a string of them here. 3 white ovals, which were observed from Earth to form in 1940 or 41. The Great Red Spot, which of course has been known for hundreds of years. A series of dark storm systems up here. Literally dozens of storm systems, and then a series of what were called barges, which you can see right here. So the system is riddled with circulating storm systems. And here is a cartoon form of what one of these plumes might be. That is, gaseous nitrogen is somehow, it manages to, like a thunderhead, to rise above its normal level and form a plume which is somehow elevated above the normal height at which the cloud forms. All right, that's the plume. The Great Red Spot itself is now known from Voyager imaging to be a large anticyclone. That means it's rotating in a counterclockwise direction. That shows up more clearly in this false color image of the Great Red Spot. And in fact, it's really this rim, this part of the Great Red Spot, which is rotating, has wind velocities of some 225 miles per hour. And the center, which looks rather different visually, is in fact has essentially no real flow pattern at all. It's sort of like the eye of a hurricane. So in a certain non-technical sense, one could describe this as a very large hurricane. Technically, it's not quite a correct description, but I think it describes the general pattern of winds, very strong winds on the outer perimeter, and the very low winds in the center. This is a cartoon form of how such a spot might form. That is, again, an upwelling region where material rises, the clouds form at their normal level. There are evidently some trace material, phosphorus perhaps, which causes the reddish color. That's a kind of a detail. It's not essential to the dynamics as far as anyone knows. And then at this altitude, of course, the atmosphere, which has risen, has to then flow back down in such a pattern. That's the kind of a simple-minded model of what this large column of atmosphere might be doing. Now, since these Voyager measurements 10 years ago, there have been a number of interesting developments. Andy Ingersoll and his students had done some calculations to suggest that if you have a lot of vortices, a lot of these small storm systems, and they interact with a big one like the Great Red Spot, occasionally they will in fact be absorbed, and a bigger spot will appear in the place of the two which were there. That has been elaborated on by Marcus up at UC Berkeley. This is a computer calculation. In this calculation, he has the interior rim of this hypothetical atmosphere rotating in a clockwise direction, and the exterior rim rotating in a counterclockwise direction. And of course, in a computer, he can change the speeds and so on. And as he did that, he found that all kinds of little vortices would develop, but over a period of time, these smaller vortices would coalesce into one great vortex. So this is now a computer calculation which in fact provides a great vortex in this atmosphere. Well, that's a model. You might say, well, what about laboratory? Given this calculation, he suggested that some people in Texas actually set this up in the laboratory, and they couldn't, of course, easily make the inner and outer edges of this thing rotate at different rates in different directions. So what they did is they have a pan of fluid rotating uniformly, but then they pump fluid in at the center and drain it out at the edge, and the net effect is exactly the same. That is, the fluid on the inside is going clockwise, and the fluid on the outside effectively counterclockwise, and notice the great spot which develops. So this would tend to suggest that spots are sort of endemic in these large atmospheres heated from below, that the small spots will coalesce into big spots. And in fact, there were spots observed on Saturn, but what about Neptune now? Well, these are some images taken by Heidi Hamel and her colleagues in 1986 of very high haze layers. This particular plot's very high altitude haze, probably indicating a high altitude methane haze, and you can see indeed evidence for some bright spots. And these spots seem to come and go. These are not great red spots or great dynamical spots, but more like plumes, I would guess. And these have been observed for a number of years by a number of observers. Here is Voyager's image of Neptune taken in January of this year. And you can see a white cloud-like feature. Now this is in the visible, which in one image as the planet rotated has rotated with the planet. Is this a plume? Is this an eruptive column of material which has carried methane up high enough in the atmosphere so when it formed a cloud it was more visible than the clouds in the surrounding regions? That's certainly one interpretation. The other thing that you can see in this image, if you look carefully, is a slight darkening behind this white cloud, more obvious perhaps in this one, but certainly quite obvious in the early April images. This is now that same region where the white cloud dominated and where you could barely see the dark spot behind it, and you can see in these images taken about 90 minutes apart that that dark spot is rotating, has about an 18-hour period. You can also see some indication that there may be a zonal-like pattern, a dark zone here. This is the south polar region, which is somewhat brighter again. But the resolution of these images is indicated by the mottled appearance here. It's still very poor resolution compared to, of course, what we will already have and what we will have over the next several months. One question is, this dark feature you see on a planetary scale is as large as the Great Red Spot is on Jupiter, and it's at about the same latitude, about 20 degrees south. Is it a dynamical vortex? Is it another great spot as there is on Jupiter and as seems to come out in these computer and laboratory simulations? Well, once we start taking regular images over the next 2 months, as we approach, I think we'll be able to find out whether this is indeed a dynamical spot, an anticyclone like the Great Red Spot, or is it some new kind of atmospheric feature which we just hasn't been apparent before. This image shows the dark spot later in April. Here is the other side of Uranus, of Neptune. Here is a bright spot which has appeared, which was barely visible 18 hours before when the same side was visible. Another suggestion of an eruptive kind of process going on. I think that one must conclude that, in fact, this is going to be a remarkably active atmosphere. It is even possible that its belt and zone pattern may not be as regular as that of Jupiter and Saturn, if in fact it is more active, that it may have some more element of chaos to it, if you like, than either Jupiter or Saturn seem to have, although Jupiter had lots and lots of localized chaos in the sense of all these small storm systems. But the next 2 months will reveal an atmosphere which I think is likely to be as interesting dynamically and visually as that of both Jupiter and Saturn. Let's now talk briefly about magnetic fields. If you like, a magnetic field of a planet can just be regarded as a bar magnet, has a north pole and a south pole with magnetic field lines looping from one pole to the other. Of course, there's not really a bar magnet inside of a planet. What's inside of a planet is a flow of fluid which has to be ionized or electrically charged, flowing in a, if you like, on the average in some sort of a loop like this, generating the magnetic field. There is no theory, no equation for a magnetic field or dynamo theory which you can write down and then plug in the rate of rotation of the planet, the amount of internal heat, etc., and out of that predict what the magnetic field should be. There is no theory. There are parts and pieces of such a theory, but there is no theory. And of course, by observing these different planets, one hopes to be able to better understand what some of the important parameters are that determine the nature of these magnetic fields. Well, we have had our surprises with these magnetic fields. In the case of Uranus, which was tipped on its side with its pole almost facing toward the sun at the time of our encounter, the internal heat source caused this region, which was electrically conducting, to convect and like little convecting cells, which you see there. And those cells, along with the general rotation of the planet, generate an electrical current, which generates the magnetic field. Our experience suggested that since the main motion of the planet is basically around this axis of rotation, that the electrical current generating the field will be more or less like I'm making the pointer go, that is perpendicular to the axis of rotation, and the axis of the magnetic field of the bar magnet will be more or less aligned with the spin axis of the planet. In the case of the Earth, our north rotational pole is only about 10 degrees from our north magnetic pole. That's the reason compasses are useful. In the case of Jupiter, also about 10 degrees. In the case of Mercury, about 10 degrees. We did have a surprise at Saturn. There it was right on axis, which in fact seemed to violate a fundamental theorem of generating magnetic fields, and did in fact require some attention to what really is going on inside these giant planets. But I think nobody expected what we found at Uranus. That is, a magnetic field which, rather than being aligned or closely aligned with the rotation axis, was tilted some 60 degrees away and offset from the center of the planet, if you like, by about a third of the planet's radius. A very peculiar current system. And there is really not yet, I think, a quantitative explanation as to how this happens. Although the suggestion, qualitative suggestion, is that we're seeing a magnetic field which is slowly tipping from this normal direction to this direction, perhaps reversing itself as the Earth's magnetic field reverses. But that's a qualitative suggestion, not a quantitative suggestion. Well, in each case then, in the case of the Earth, here is its spin axis, there is its magnetic axis, very closely aligned. Here is Jupiter, spin axis, magnetic axis closely aligned. Saturn, all exactly aligned, and then Uranus off axis by 60 degrees. The field values at the surface of the Earth, about 0.3 Gauss here. Jupiter's 4 Gauss, more than 10 times stronger. Saturn was about 0.2 Gauss, and Uranus at its equator was about 0.23 Gauss. So all in the range between 0.2 and 1 Gauss. And if you had to ask, what do you think Neptune's field would be? Surprise, between 0.5 and 1 Gauss. I mean, those are the fields we've seen, and therefore those are the fields which, in fact, we expect planets to be able to generate. If you ask, what does one expect in the way of alignment? I think most would say, well, Uranus is peculiar because it's tipped on its side and its polar region is warmer than its equator, and that's affected the interior fluid flow in the planet. Neptune is more normally aligned, and therefore the magnetic field should be more normally aligned. That's the best guess, but I think so far our guesses in the case of Saturn and Uranus were both wrong. So we'll find out about Neptune shortly, about a day before closest approach. Now here is a schematic cross-section of what happens to that magnetic field, which starts out as a bar magnet field with the field lines looping like this. As they get further and further from the planet, you might think the field lines would just extend to infinity, but there is an ionized gas blowing from the sun, a plasma, at about 400 kilometers per second, 1 million miles per hour, and that ionized gas overwhelms the weak magnetic field out here and compresses it down to the point where the field is strong enough to hold it off. And the net result is the field, which starts out very symmetric, ends up being blown into this windsock-like shape. There is a magnetotail, as it's called. One of the interesting things about our Neptune encounter is it will be our first and only flyby through what we think, if the fields are aligned with the rotation axis, is the north polar cap of the magnetic field, this region right here, where, as you notice, the field lines, rather than closing back to the other pole, go back down the tail. And it's exactly these open field lines where the particles stream in along the field lines from outside to cause the aurora. And in the case of the Earth, for instance, if you look down on the Earth, you see a beautiful auroral oval, which is the foot of the field lines which demarcate the outer surface of this tail. Here is, in fact, an image, Lou Franks from the Dynamics Explorer. Here is North America, as you can see. This is taken in the ultraviolet, a beautiful auroral oval. All the magnetic field inside of this oval forms the tail of the Earth, magnetic tail. All the magnetic field lines down here close down as loops to the other part of the atmosphere, other part of the planet. And as I said, Voyager will fly 5,000 kilometers above the cloud tops right through this region. I think it's going to be really a very interesting set of measurements to both look at the UV formation of the auroral oval and to measure the particles which are streaming down to cause the aurora. It'll be the only passage to this region in a giant planet. The only one that's planned probably, there's no one planned for decades beyond this. A unique opportunity. Well, what about rings? Saturn's rings, of course, have been known ever since Galileo, although he didn't really recognize them as rings. Voyager really provided an immense wealth of detail of what's going on in the rings, some of which we understand and some of which we still don't understand. But it's now very clear that, for instance, the outer edge of the B ring, which you see here is very sharp, is maintained by the moon Mimas, which is out here, which orbits Saturn once for every twice that the ring particles at this distance orbit, and the particles run into a resonance. They just can't move out. They run into Mimas's resonance push, which pushes them back in. And so the basic outlines structure of the rings is believed to be controlled by the larger moons outside. But there are also some finer details which are controlled by moons, such as the F ring, which was discovered by Pioneer 11 in 1979. And by the time Voyager got there in 1980, there was a model which had been produced by Goldreich and Tremaine, which said, to know if you have a narrow ring like that, you must have two small moons, one on each side of the ring, shepherding the material, maintaining it, pushing the material back into the region between the two moons. Otherwise, this thin ring will quickly dissipate in a very, very few years compared to the life of the solar system, to the age of the solar system. Here are those two moons, the two shepherding moons, shepherding the narrow F ring. Well, Uranus was really the reason that, in fact, that theory had been developed, because in 1977, Jim Elliott and his collaborators had observed a star going behind Uranus. This is Uranus, except it's been blotted out in this image, Voyager image, because it's so much brighter than the rings that you can see here. A star was being observed to study the atmosphere of Uranus, and as the star approached Uranus, they noticed the star blinked on and off a number of times. Then it went behind the planet, came out, and blinked on and off again. And it didn't take them long to realize that they had, in fact, discovered a series of 9 narrow rings orbiting Uranus. One of the problems with these Uranus rings is that they're charcoal black. And this image is very poor quality because it took a very long exposure to be able to see the ring systems. And even so, you cannot see all 9 narrow rings in this image. You can see more of the rings in this image. And in fact, here is the outermost ring, and there are the two shepherding satellites again. So again, we seem to have this important role between the satellites, the small objects, and the dust or rocky, the smaller gravel-like objects which make up the rings themselves. It's now becoming more likely, many now believe that it's more likely these ring systems are the result of a recent catastrophe rather than something which formed at the time the planet formed. That there used to be, for instance, in the case of Uranus, a larger moon in orbit. there was a catastrophic collision. It broke up into many pieces. The larger pieces became the small moons, and the smaller pieces then were trapped between the moons to form the narrow rings. Well, what about Neptune? Different yet again. A number of stellar occultations have been done tracking a star going behind the planet like this many, many times, and only one time in 10 has any material been found to block the starlight away from the planet. And never has it been observed that the starlight was blocked on both sides of the planet at the same radius in the same stellar occultation. This has led to the conclusion that there are no complete rings of dense material around Neptune at all. There may be little short fragments, which are in this computer graphic indicated here, ring arcs, which somehow are maintained in these localized regions around Neptune. If I could have the view graph now, I can just quickly show you where those regions are. Here is Neptune. This is Neptune's equatorial plane. We believe they're in the equatorial plane, although that's not known. That's the best surmise, best hypothesis. And here's one Neptunian radius, and these ring arcs that have been detected are located in these three regions. And there's anywhere between 3 to 5 or 6 arcs which have been detected, depending on how carefully you ask that the detection be verified. Voyager will fly by through the ring plane at this radius right here, just outside the outermost known ring arc. Now, the one question is, how do you maintain, if you have a complete ring of particles around Neptune, you can do that by putting a shepherding satellite on each side. But how do you maintain localized blobs of material? One suggestion, which again Peter Goldreich and his colleagues have been responsible for, is related to the L4 and L5 point, which many of you have heard about, which are characteristic points in a moon's orbit around a planet. In the case of this, the Earth's moon, 60 degrees in front of the moon and 60 degrees behind the moon in its orbit, there would be the L4 and L5 position. If you put something there, it would sort of stay there and orbit in synchronism with the moon. That doesn't help, though, if you have these ring arcs at different radii, and you have to, in fact, you cannot really keep a ring at that position. You can only keep one solid object there. And so Goldreich has suggested that, in fact, rather than having a moon shepherding these rings, if you like, in the plane, you incline it some 20 or 30 degrees with respect to the plane of the equator, and that introduces a whole set of little catch basins, if you like, which then can trap material. He thinks there might be literally 50 to 100 of these little locations where ring material has been captured. And so here is that moon, which is drawn in the plane of in the equatorial plane of the planet, but in fact must be out of the plane above on this side, and then as it orbits, it goes below on this side, and it generates these various locations, which are equivalent, if you like, to the L4 and L5 points in the Earth-Moon system, but there are many more of them, and they're very restricted in longitude. Perhaps these will be the ring arcs. Well, we'll certainly find that satellite if it's there. It's got to be 40 or 50 kilometers in radius at least in order to do the job. And there's some hope that even though these ring arcs are probably charcoal black, that we will be able to image them. Anyway, in any case, we know it's different, and most likely there may be some surprises. What about the satellites? Well, we know of two for sure. Here's Voyager's inbound trajectory. This is where it flies over the North Polar region through what we believe will be the auroral zone, and then down to an encounter with Triton right here, and then out of the system. There is one satellite, Nereid, which has a very peculiar orbit. That is, it's a highly eccentric orbit, remarkably eccentric orbit, and that's a bit of a puzzle, and it's in an inclined plane. So the question is, how did that come about? And there is a model, which I'll come back to in a few minutes, which Goldreich and his colleagues have developed to explain why Nereid is in this peculiar orbit. That's related to why Triton is in its peculiar orbit. Here's a more close-up view. Here's our flyby down to our closest approach with Triton. Here's where the ring arcs are. Triton is very unusual in the sense that, first of all, Neptune's spin axis is tipped back a bit well, you can see the equatorial plane is here where the ring arcs are. Its spin axis is tipped back about 30 degrees, so the sun is illuminating its south polar region. Neptune is in an orbit which is further tilted by 20 degrees with respect to Neptune's orbit, so it's in a very inclined plane, and it's in a retrograde motion. That is, Neptune is rotating like this, just as the Earth is. Triton is going around the opposite direction to the rotation of the planet. It's believed that when satellites form in orbit around a planet, they have the same motion as the disk out of which the material formed. That then immediately suggests that Triton did not form in place around Neptune, but was captured. And it's that capture which can be a very important part of the story of the evolution of the system. But before I talk about that, I want to talk about another peculiar aspect of Triton. That is, its spin axis will be perpendicular to its orbit plane, so it will be inclined with a spin axis like this, where the sun is coming in strongly on its south pole. And we're now approaching, around the year 2000 would be maximum solar heating of the south polar region of Triton. And in the last few years, there have been indications that the atmosphere on Triton has begun to change. The suggestion is that, in fact, we know from Earth-based data that Triton has methane on its surface, solid methane, or in its surface or in its atmosphere, most likely both places, depending on its season. There is even suggestion from ground-based data that there may be nitrogen on its surface. There is a debate as to whether the nitrogen can be in liquid form or in solid form, but there seems to be some suggestion that there is nitrogen there, and that would almost certainly, if that's true, mean there's a nitrogen atmosphere. Here is not the polar cap of Triton. This is Mars, but I used it to make the point that if methane is there in solid form and nitrogen is there in solid form, it may well be primarily in the polar regions. And as this season varies over a period of almost 200 years, going from south to north to south, that the one polar cap will evaporate, and the evaporated gases, methane and nitrogen, would then transport to the other polar region, which was in the dark, and freeze out, just as on Mars. In other words, the atmospheric pressure on Triton can vary dramatically, as Larry Trafton suggested a number of years ago, dramatically over its season, which is a very long season. We happen to be approaching it at a season when it's near approaching southern summer, where the southern polar cap may be evaporating or may have evaporated totally. We don't know. But it's likely to be a very exciting encounter. Now, this artist sketch was put together some years ago to sort of illustrate the fact that there could be lakes of liquid nitrogen on the surface. The surface is probably mainly water ice, but it's got some methane ice on the surface, and it has a reddish-orange residue in this picture because the methane in the atmosphere of this object is being photolyzed by sunlight. Complex hydrocarbons are being formed out of the methane which is there. And that, as those hydrocarbons become larger and larger and polymerize, eventually they will settle down on the surface and form a coating. In fact, Dolitsky and her colleagues have suggested that even if there were lakes of liquid nitrogen, they would be covered with a oil slick, not from Exxon, but from Triton's own atmosphere, having made these hydrocarbons which then form a thick layer of lighter than nitrogen material which floats on the surface. A very interesting scenario. Well, we have seen one other object where there's a lot of photochemistry. That's Titan. In fact, there was so much photochemistry going on in Titan's atmosphere at Saturn that we couldn't see the surface. Ground-based data suggests that that's not the case for Triton, that in fact there's a photochemistry, but it's not so active that it produces an opaque atmosphere. Triton's atmosphere was really opaque. We could not see through the photochemical haze, the hydrocarbons. Here's what we learned about its atmosphere, though, and indeed it was mainly nitrogen. So maybe Triton will be like this, but it did have the methane, which was essential to making all the complex hydrocarbons which are observed in the haze layer and which undoubtedly have formed a very thick layer of material on the surface of Titan. So this is the parent material out of which all of these and many, many more are made, and of which this one in particular is made in such quantities that at the temperatures and pressures on Titan, it forms lakes and oceans of liquid ethane on the surface of Titan, which are made photochemically in the atmosphere of Titan out of the methane. Well, exactly what's going on Triton, no one knows, but I think that the prospects of an interesting photochemistry are certainly there. Well, what about the capture of Triton into orbit around Neptune? Now, you might say, why do I show a picture of Uranus if I'm going to talk about Triton? It's because I want to make the point that around Uranus, there is a series of regular satellites. This is an image taken by Terrell and Smith some years ago from Earth. Here's Miranda's orbit, here's Umbriel's orbit, there's Ariel, all in circular orbits, orbiting around Uranus like this. And you might ask, why doesn't Neptune have a regular satellite system? Jupiter has one, Saturn has one, Uranus has one. They all have regular satellite systems formed around the planet, yet Neptune does not have one. Goldreich and his colleagues suggest that's because of Triton. That is, Triton came in, if you now regard this as Neptune sitting here and all of its satellites which formed, Triton came in, ran into one of the satellites, that, as a result, lost enough energy and angular momentum that it then was captured into a very elongated orbit like this. But it orbited Neptune time after time and occasionally would hit that satellite and absorb it, and occasionally hit that satellite and absorb it, and over a period of 1 billion years would have essentially accreted all of the regular satellites that were formed, that had been formed between about 5 radii, which is about where Miranda is, out to where Titan is today, which is 14. And in fact, the prediction is we really ought to find nothing in that system, in that region, because Triton, it's all inside of Triton now. In the process, you might imagine Triton itself suffered some difficulty, and the calculations suggest that Triton remained liquid for almost 1 billion years after it formed. Most of these objects form, and of course during the formation, during the accretion of the material, they melt, but they're small, it's very cold, and they quickly radiate away and freeze and essentially become inactive objects. And let me just give you an idea of some of what we might expect to see on Triton or what we might not expect to see. This is Callisto, half water ice, and its surface is essentially has been unaffected by any internal heating processes. That is, there are no canyons, there are no fault systems, there are no volcanoes, there are none of the evidences of a tectonic activity, just heavily pockmarked by impacts from outside. Just like, for instance, up close, this region of Rhea. Just a surface which is probably froze very early on within a few hundred million years, within 100 million years or so of its formation, and then was impacted while there were still lots of debris around early on in the life of the solar system. It's unlikely Triton will look like this because it was liquid at the time all these particles were in orbit around the sun and around the planet. So it's unlikely Triton should have such an ancient-looking surface if it was liquid for almost 1 billion years. Well, perhaps it will look like Ganymede. This is a neighbor at Jupiter of Callisto, about the same size, but clearly looks different. There are these larger regions, which are the old crust, probably not unlike the entire crust of Callisto, but it's separated by lighter material, which is striated. And this lighter material, and you can do crater counts to see how many impacts there are fewer impacts on the lighter material than on the dark, indicating it's lighter, and it may be a few 100 million years lighter. That is, there was some internal heating which modified the surface, the original frozen surface of Ganymede in a major way, replacing half of the old crust with a newer crust. But that all took place in a few 100 million years. Maybe we'll see something like that on Triton, but maybe Triton was even more active than Ganymede. What other examples have we got? Well, here is Ariel at Uranus. And the main thing I want to concentrate on is this large canyon system up here, which is believed was formed because perhaps Ariel, as it cools off, of course, the outer crust freezes first, and then the inner part, which is liquid, eventually freezes. And we all know that as water freezes, it expands. And as it expands, it cracks the crust, just like it cracks the water pipes. And this view of the canyon makes it very clear that these are major structures. This canyon is about 50 kilometers wide and 25 kilometers deep, much, much larger than the Grand Canyon, even though this is a very tiny little icy moon. Well, we see such things as this, which occurred as Triton cooled off from its extended period of heating. Or will we see something like this? This is Miranda, which has on one face, has 3 major regions which were tectonically modified by some mechanism, even though this moon is only 300 miles across, 500 kilometers across, and has a scarp, an offset, a cliff, if you like, some 20 kilometers high. Will we see something like this? After all, this is a very tiny moon. Triton is almost certainly larger than Miranda. Well, we're unlikely to see volcanoes, though. This is Io. Io is still liquid on the interior. Perhaps, though, at the time Triton was being heated for a period of 1 billion years, it may well have had some activity very similar to that which is currently occurring on Io. But it's certainly true that if we look at Triton today, it's in a very stable orbit, it's not being heated, and so we do not expect to see volcanoes. But will we see any evidence that there was at one time volcanic activity? I don't know. I'm just throwing out a lot of speculations, which we'll all know the answer to in less than 3 months. And that's what makes it so much fun. So I think with that, I'd like to close and just say the next 3 months, I think, are indeed going to be exciting. Thank you.